So we're going to do a little bit of practice involving some nice, very simple physics applications. Nothing too scary. We're still beginning. We're newbies at this. We'll get better. We'll get better. Don't worry. But it's good practice to do these, partly because it's good to do word problems. A lot of people have this unnatural fear of word problems, but we should like words. We use them almost every day. And so we need to get better at doing word problems. The other thing we're going to talk about is when can we be confident that solutions exist? And we'll see that under some very reasonable assumptions that yes, solutions to our differential equations will exist. So yay for us. All right, well, let's begin. So in our first problem, we have a spacecraft which is heading to the surface of a small moon. So small, we can ignore its gravity. Now you probably think to yourself, that's no moon! Well, it's a small moon. All right. Now, the spacecraft is traveling at 1,000 miles per hour. So, all right, pretty fast. And it has rockets, which can slow it down at a constant rate of 20,000 miles per hour squared. The question, at what height above the small moon should the rockets start to fire to ensure a soft touchdown? All right, good. Now, at this point, you might say, well, I see math insofar as I see numbers. I see these numbers here. So, kind of mathy, right? But there's a lot of things that aren't being said here explicitly. So let's take some time to understand what the question is asking us to do. And then we can be like, okay, let's go forward. So first off, this notion of a soft touchdown. Let's make sure we understand what that means. So there's a couple of scenarios that could happen as we're approaching our small moon. So here's our surface of our small moon. And, what could happen? Well, one thing that could happen is that when we come in on our little spacecraft here, we don't fire our rockets soon enough. And so what happens is we hit the surface, not very softly, we crash. Our small moon becomes slightly less small. We become a part of the moon. Okay, we don't want that. So that's what happens if we wait too long to fire our rockets. Now, what would happen if we fire our rockets too early? Well, what happens is that we get to slow down, and actually we end up slowing down and sort of hovering above the surface and then go back out into space. So that would be if we don't fire our rockets, or rather we fire our rockets too soon. Okay, so what's that sweet spot? What's that, oh, just right kind of landing? Well, it's when we have our spacecraft and we come down, and when we're at the surface, our velocity is 0. That's what we want. Because then we'll be able to say, look, we're on the surface, but we didn't hit it, so it was soft. All right, so our goal, when we say a soft touchdown, we say, okay, we want to have our velocity be equal to 0 at the surface. Okay, so now we say, all right, well, that feels a little bit more mathy. We've introduced this sort of concept here. Let's go back and look at those numbers we talked about before. We said, hey, we have numbers. They feel like math, right? Okay, so let's first deal with this 1,000. What is that capturing? So our spacecraft is coming towards the surface at 1,000 miles per hour. Well, it's our velocity. But it's not a constant velocity, right? It's just saying our velocity is 1,000 miles per hour, and then we're going to turn on our rockets. All right. So what we can think of is that this is a velocity when we start the procedure, when we turn on our rockets. Another way to say it is this is like our initial velocity. So we oftentimes write that as v0. So think of it as at time 0. So v0 is 1,000. And you'll notice I'm not going to write down units. Generally speaking, units have a nice way of working themselves out. And so we won't worry about units. So, all right. So when I say we don't worry about units, we won't worry about units in the intermediate computations. And at the end we'll say, and here are the units. All right, good. So we have our initial velocity. What about the 20,000? All right. Actually, hold on. Let's be careful with our initial velocity, because I just made a small mistake, and I want to fix it. We have to worry about the sign, right? Because, well, the question is our velocity positive or negative? Now, this is not just a something like, well, we just shrug our shoulders, make it whatever it is. Think about the context. So what's happening? We're coming towards the surface, right? So if we're coming towards the surface, what we care about is how are we relative to the surface. If we're getting closer to the surface, that means our distance is shrinking. And so our velocity needs to capture the fact that we're decreasing. So actually, should have been negative 1,000. So the negative is to say we are going down. All right. Okay, there we go. All right. All right. Now what about the 20,000? Well, 20,000, that has something to do with how the velocity changes, and it's an acceleration. You can even see it in terms of the units here, because it's talking about miles per hour squared. Okay, so this is a acceleration. Now, what kind of acceleration? In other words, is it an initial acceleration, or are we always going to be accelerating at this same amount? And so the answer is it's going to be a constant acceleration. Now you might say, well, how do you know it's a constant acceleration? Well, it tells us that it's a constant. It's a pretty good hint, right? Read the problem. It has nice words in it. Okay, so we're not going to write A0. We're going to write our just acceleration at any given time is 20,000. Now, just as we did here discussing the plus minus, we should also have a discussion about plus minus as well. So is acceleration positive or negative? Again, think about what we're trying to do. Well, what we're trying to do is we're trying to slow down our velocity, which means we're trying to get it to zero. Well, since it's negative, to get it to zero, we need it to actually go up. And so our acceleration should be positive. Now, another way to think about the fact that acceleration should be positive is think about our rockets. If our rockets are firing here, which way is acceleration pointing? It's pointing away from the surface. So we're moving away, so it should be a positive acceleration. Just as, since we're moving towards the surface, velocity should be negative. So it's the relative to the surface that helps us determine plus or minus. All right, great. So now we have a formula for acceleration. We say, well, let's find the formula for velocity. So our formula for velocity would be integrate 20,000 times t plus some constant c. All right, well, how do we find the constant? Well, to find the constant, we use some knowledge of what we have going on. So in particular, we can say, hey, we know what's happening at time zero, that our velocity should be negative 1,000. And so we can say, well, look, negative 1,000 should equal our velocity at time zero. Well, all right, that's 20,000 times 0 plus c. Well, all right, c is negative 1,000. Great. So now we've come to our conclusion. Our velocity function is 20,000 t minus 1,000. Wonderful, wonderful. All right, good. Now, what's next? Well, we know we're looking for a height, which means we really are after a position. So we should find the position function. All right, well, we can do that. When we start with acceleration, we integrate it to find velocity. If we start with the velocity and we integrate again, we find position. So we say, okay, well, let's do that. So our position is what? You integrate, say, all right, look, antiderivative of 20,000 t. Well, it's 20,000, and then you take a half t squared. Okay, so that would be 10,000 t squared. Antiderivative of 1,000, all right, that's 1,000 t. And then another constant. Now, we've already used the constant c, so just to keep sure that we don't have anything ambiguous, we use a new constant. We like to work our way through the alphabet, so we're after the symbol. Next symbol would be D. Now, what is it we want to find? Well, we want to find when did we fire the rockets to get a soft landing. So, in other words, where were we at time 0? Because we're thinking of turning the rockets on at time 0. And we say, oh, well, okay, at time 0, that would be what? It would be 0 minus 0 plus D. We say, aha, there's our answer. We want to be D miles up. And now we're like, that's a terrible answer because you haven't answered the question at all. Because we don't know what D is. And yeah, you're right, we don't know that. So now we have to think about what's going on. Well, what is going on? Come back to this part right here. We haven't used this yet. What does it say? It says we want our velocity to equal 0 when we're at the surface. All right. So that tells us, okay, we can use this information to gain some insight into our problem. So what can we do? Well, it's saying something about velocity being 0. And so we can say, all right, well, let's start with our velocity function. And we'll set it equal to 0. So 0 would be 20,000 times t minus 1,000. Or we could say that t is equal to 1,000, right, because you add 1,000, and divide by 20,000. All right, sure, we can do that. Of course, now it's like, that looks like a not fun computation, until we say, well, wait a second, we can knock off the zeros really quickly. And so we say, oh, okay, that's not so bad. And so we really say, aha, insight. That says we're going to be at the surface in 1/20th of an hour, because our measurement for time is an hour. So in other words, it's going to take us 3 minutes to do our descent. All right, now that's good information. Well, what else is true when we're at the surface? So when we're at the surface, another way to say that is that our position is equal to 0. So we say, all right. So we come in and say, all right, 0, our height, will happen when we're 1/20th of an hour in. Okay. So plug it in, see what we get. So that's 10,000 times 1/20th squared minus 1,000 times 1/20th and plus D. Now, if you take 10,000 divided by 1/20th squared, well, you can think of it as 10 squared is 100, right? And so you can knock off 2 zeros, and then 2 squared is 4. 100 divided by 4 will give us 25. Again, you can come here, you can knock off a 0, and then say it's 100 divided by 2. All right, that's 50. And then, of course, D is D. Great. So we come to our next thing, which says 0 equals 25 minus 50 plus whatever D should be. And that's enough information for us to say, aha, we can solve for our constant. We can find what D is. So what is it? Well, you see, 25 minus 50 would be negative 25, so we would need to have D be positive 25. All right, so D equals 25. Now, what are the units? Well, it's our distance, so it's 25 miles. And there we go. That's it. We're done. So there's our answer. We need to be 25 miles above the surface at the point when we fire the rockets. And if we do that, we're going to come down, and right when we hit that surface, we're going to have changed our speed to 0. That's a great way to land our spacecraft. Good. All right. That wasn't too bad, right? Yeah, of course not. Just be patient, work through what it has. And let's think about, what do phrases mean? What is a self-touchdown? Notice that, okay, there's a constant. All right, that tells me something about it's a constant function. And piece things together and build up slowly. And you get your answer. It's not about being fast all the time. It's just about understanding. Understanding, patience, and we'll get to our answer in the end. All right, well, that was a good problem. Let's try another one, right? Sure, there's always more problems out there. All right, so this one's a little bit more action-packed. So a bomb is dropped from a helicopter hovering at an altitude of 800 feet above the ground. And from the ground directly beneath the helicopter, a projectile is fired straight upward toward the bomb, exactly 2 seconds after the bomb is released. With what initial velocity should the projectile be fired in order to hit the bomb at an altitude of exactly 400 feet? All right, so this is, like I said, very action-packed thing going on here. So there's a lot to process, so let's visualize what's going on. Because I think if we can visualize, then it helps us understand the problem. And you should always understand a problem before you try to solve it. Because if you rush in without understanding, then pretty soon you'll have lots of computations, but they may not be the ones we need. Okay, so let's visualize. So there's really 3 events that happen in this problem. So the first event says that you have this helicopter, so we'll draw a rough helicopter here. So here's our helicopter up in the air. And what happens is that it's currently 800 feet. Okay, that's fine. So it's 800 feet up, and it drops a bomb. All right. And so notice it doesn't throw a bomb. It doesn't, shoot a bomb. It drops it. All right. So that's going to be important. Now, let's say this happens at time 0. Okay. The next interesting thing to happen is 2 seconds later, right? Because it's exactly 2 seconds after the bomb is released. Now, what's happened? Well, there's the helicopter up here. All right, great. And what's the bomb done? Well, it's dropping. It probably doesn't drop a lot in 2 seconds, but it's moving down. Okay, so it's gaining some speed. It's moving down. And then in the meantime, the projectile goes up. So we say, oh, all right, great. So now our projectile is going to launch upward. And now what's the third event? So the third event, well, that happens at some time, but it doesn't tell us what time. Our helicopter, probably still up here, hasn't really had a lot of time to move. And we see, lo and behold, at 400 feet, that the bomb has dropped down. By this time, it's picked up a lot of speed, so it's moving even faster than it was before. And the projectile is up right at the same point to meet it. Okay, and there we go. There's the 3 events. We drop the bomb. A little later, we fire the projectile. A little later, they come together. All right, great. And so now we've got to figure out, okay, what do we have to figure out? Well, we're after a velocity. So with what initial velocity should we have fired? So our answer is going to be a number. And all right, where to begin? Well, we really have 2 objects here. And let's start where the first object starts. We'll start with our bomb dropping. All right, so we'll start with the bomb. Okay, so here we go. So what can we say? Well, let's think about what's true. When we drop the bomb here, what's some information that we know? So for instance, we dropped it. And so when we start, what's the velocity? What is it? 0. It doesn't have any velocity. Okay, so we know our initial velocity is 0. How about position? Do we know from how high we dropped it? Well, yeah, that's part of the problem. We dropped it from a height of 800. So our initial position is 800. Wow, that's amazing. Great. Now, what about acceleration? Okay, so when we drop it, what is acting on the bomb? What makes it drop? Well, the answer is gravity. Gravity is what's pulling it down. So our acceleration is gravity. Now, the good news is we know something about acceleration, or I really should say we know something about gravity on Earth. We spent a lot of time here. We've been studying it. We've gotten pretty good at it. So what is our acceleration? Well, we have to be careful, right? Because there's sort of two constants depending upon what units of measurement we are. If we measure in like meters per second, it's one constant, 9.8 something, I think. I'm not a physicist. I'm sorry, I don't know. But we're not measuring in meters. No, see, everything's measured in feet. So what do we use? Well, when we're measuring things in feet, we use 32. Now, that's not the most accurate measurement, but it's a really good number. It's easy to work with. So we use 32. So our acceleration is 32. Now, notice, it's not that our acceleration initially is 32. It's our acceleration is always 32. So we can say, hey, our acceleration function is gravity, and that's 32. But acceleration pulls down. It's pulling towards the ground, so we actually put a negative 32. All right, so this is our gravity. The gravity of the situation. Okay, great. Well, notice because we have the acceleration and we have some initial conditions, we can actually recover the velocity function and the position function. So let's do that. All right, so let's start with velocity. What can we say? Well, our velocity, it's the antiderivative of acceleration. Okay, so we're going to integrate our negative 32, and we say, all right, velocity would be negative 32t plus some constant c. But we can use our initial condition. We say, all right, velocity at time 0, which is our initial velocity, is 0. Well, that's negative 32 times 0 plus c. And so we say, aha, c is 0. Well, yeah, we kind of knew that. Velocity should be 0. And so we say, great. So our velocity function will be minus 32t. All right, on to position. Well, okay, what happens there? Well, we integrate velocity. Say, all right, well, our position function, s of t, will be integral of minus 32t. It's minus 32 over 2, which is 16, t squared, plus a new constant. All right, it's not c, so we got to go through our alphabet. So we'll use d as our constant. All right, great. And, well, now what? Well, we know our initial position. So our position at time 0, which is our initial position, is 800. So that's minus 16 times 0 squared plus 800, which means that our position function is 800. We say, ha, great, wonderful. So we come to the conclusion that for the bomb, that our position function, we can write it as s of t is equal to minus 16t squared plus 800. Now, can we use this to find anything out? So we could use it to say, all right, where is the bomb at 2 seconds? Okay, sure. Take 16 times 2 squared. 16 times 4 is 64. 800 subtract 64 was 736, I think. All right, so we're at 736 feet up after 2 seconds, which helps us somehow, maybe. That's not so clear. But now look here, because this is a place where we do know how high the bomb is, right? It's at 400 feet. So now, instead of using the function to say how is the height at a certain time, we can use the height at a certain time to figure out, well, which time was it? So in other words, it's using height to find time and not time to find height. So we say, great. This is kind of our great, So what we can do is, well, all right, we need a little bit of space here to do this computation. So we say, okay, we can say, look, when we're at a height of 400, so that's at some time, we don't know what it is, and that's minus 16t squared plus 800. All right, well, now we've moved stuff around. So we can move the 16t squared over, we can move the 400 over. We get 16t squared equals 400. And then we divide, and we can sit here and ponder, use the calculator, or we can say, aha, 25. Yeah, it is. It's 25. And so that tells us that our time is 5. Anyway, I say, wait, what about negative 5? No. We think of time as moving forward in the problem, right? Because we said, look, time marches on. So we say, aha. So that says at time 5. At 5 seconds after the bomb drops, that's when the bomb and our projectile come together and make a nice explosion. All right, great. Now, we haven't answered the question, but we've gained new information. That's good. Gaining new information is a very useful thing to do. All right, so where to next? Well, we've pretty much tapped out everything we could from the information about the bomb. So that means the next thing we should do is let's look at the projectile and see, okay, what can we gain from that? Well, let's take a look. What do we know? Well, we know some things about the projectile, namely at time 2, right? It says, all right, that's when we launch it. And so it's at a height of 0. The acceleration is still gravity, and then there's some initial velocity. And then at time 5, they need to collide. Now here's where things get like, this is kind of messy, because now we have to use not time 0. See, time 0, we love 0. 0 is such a nice number to work with, because 0 makes a lot of expressions simplify. That's why we like 0, it's just because it's the great simplifier. So what can we do? Well, we can bite the bullet and say, all right, let's just deal with our time as it is. Or, and you can tell this is where we're going, we can think about re-indexing time. So really I could say, look, this time, where we use a lowercase t, that's from the perspective of the bomb. But the projectile doesn't care what happens with where the bomb dropped. It really says, look, I care about what happens when I get to come in. And so from its perspective, this should really say, look, instead of this being at time 2, we'll think of this as time 0. So I'm going to use a new symbol, capital T. So that's the time from the perspective of the projectile. And then say, look, 3 seconds after it launches, that's when we're going to hit. All right. So what do we get? Well, so we have our acceleration, still just gravity, so still negative 32. Our velocity at our time 0, because we're now in our new time, so we can still call it time 0. Well, we don't know. That's to be determined. In fact, that's what we're after. But we do know our position at time 0. We're at 0, because we're launching from the ground. All right. Well, so now we can say, okay, we start, say our velocity function, well, integrate negative 32t plus another constant, well, okay, I'll call it e, but we can plug in our initial conditions and say, oh, well, that really says that our velocity at time capital 0, whoops, I need to put this as a capital T. I'm sorry about that. Good. All right, problem fixed, right? So our velocity at time 0, well, that's capital E, and that's what we're after. Okay, so we'll call this E. We can call this V naught. Okay, great. So, well, all right. Now, what can we say about our position? Our position, negative 16t squared plus whatever this number turns out to be times t plus some constant f. But we know that our position at time 0 is 0. And if we plug 0 in to this right-hand side, a lot of simplification, and we'll get 0, 0, f. So we say, aha, there we go. So, what have we learned? Well, hopefully we've learned enough to help us get to the problem's answer, because we're running out of space. But we're close. We're close, right? Because now what do we have? Well, we can say, look, our position at any given time t is negative 16 t squared plus e times t, where e is our answer. And once we have the value for e, we're done. And then we say, and we have a piece of information that hasn't been used yet. Namely, we know where we're at time 3. At time 3, we're 400 feet up. So 400 equals our position at time 3. So that's negative 16 times 3 squared plus e times 3. Now, 16 times 3 squared, that's 16 times 9. And 16 times 9 is 144, right? And what's that? It's gross. All right, so sometimes you'll hear there's a phrase called one gross, which is a dozen dozen. So a dozen dozen is 12 times 12 is 144. So that's what, a gross. Okay, it's a little bit of math humor. A little tiny bit of math humor. Okay, so that's 144. We can move it across. So we end up with 544 is equal to e times 3. And then we say, okay, now divide by 3. So we get that e, which is what we're after, right? That's our initial velocity. That's where our velocity of the projectile is when it launches. That's 544 divided by 3. And we say, okay, 544 over 3, also written as 544 over 3. Yeah, 3 doesn't divide into 544. It's not a multiple of 3. And what are the units? Do we know it? Well, we can see distance has been measured in feet, and time has been measured in seconds. And really, because of the type of units we use for gravity, it should be feet and seconds. So 544 thirds feet per second. And we're done. That's the answer. That's the answer. Wow, good. Now, if you think back about all these computations, if you look at any single individual computation, nothing was too bad. They're all pretty straightforward. What makes this kind of problem challenging is figuring out how all the pieces come together. So when you're working on a problem, it can be an advantage to say, let me back off for a second. Let me make sure I understand what's going on. How does everything fit together? And drawing pictures is a great way to do that, because you say, oh, okay, I see how all these little pieces move and come together, so I can piece together the situation. And there we go. Wow, what a fun problem. What a fun problem. All right, well, enough examples. Now on to the real topic that we want to talk about, which is something about when can we be confident that there is a solution. Now, we may not be confident in that we can find it, but we can talk about, hey, there's at least a solution out there. So this is a background fact. In the book, they call this a theorem. And a theorem is basically just a nice statement of a mathematical fact. Now, for us, we're not going to worry too much about why this works. We're just going to accept it on, I'll say trust. I didn't want to say faith, because I don't want to make math sound like a religion. There are details, and we're not going to get into them. So I just want to be upfront about that. If you like knowing the details, there's lots more advanced classes out there. I'll go through and explain it. We'll do a little bit of hand waving in just a moment to say, this is the intuition about why. All right, so what do we have? Well, let's start by saying our basic setup is we have a differential equation with some initial conditions. So y prime equals f of xy, that's our differential equation. Our initial condition is y of a equals b. Notice this is what we've called the normal form. So in other words, we've taken our first order differential equation and isolated the y prime by itself. In practice, that might not always be possible, but let's just assume that we're working with one that is, and say, okay, so here we have this wonderful setup. Now, the first statement says, if our function is continuous, all right, we should pause and make sure we understand all these words. So, when is a function continuous? Do we remember that? We talked about it before in various classes, and depending upon where you learn about continuous, you might have heard different definitions. So some people like to say, oh, a continuous is something you can draw where you don't have to lift your pencil, right? If you have to lift your pencil, that's not continuous. It's not a bad intuition. So the way I like to think about continuous is, namely, continuous means there's no surprises. So that is, what you expect to be true is what's true. Now, what would be a surprise? Well, a surprise would be like a hole. That's a surprise. So that's an example where something isn't continuous. Or you could even have like a hole where it's filled in but not in the right place. Or you could have a jump. That's a surprise. That's an example where something is not continuous. Or you might have some kind of an asymptote going on. So these are examples of things that are not continuous when you have surprises. The formal definition says that as you get close, in other words, as you take the limit towards a point, the limit is the exact same as what the function is at the point. So that's what we mean by no surprises. Okay, and on a side note, pretty much any function you write down, unless there's some sort of weird asymptote or some division by zero, most of the function expressions that you'll write down, that'll be continuous. Okay, so if our function is continuous, near AB, so you should really think of it when we talk about near AB, it says near our initial conditions. Then the conclusion is there's at least one solution to the differential equation. And so we say, great, at least one. In other words, this means we can guarantee existence. We can guarantee that there's a solution that exists. Now, there's a little caveat here, which holds near x equals a. So we don't say it's going to work for everything. Our solution may not exist for all values of x, but it'll work for values close by. All right, so what's kind of the intuition here? Here's how I think about it. And what we have is we say, okay, great. Look, we have our initial input A, our initial output B. So we're looking for our curve that satisfies y prime equals f of xy and passes through this point, AB. Now, what do we know? We know our assumption says that, hey, our function is continuous nearby. So that says, in some space around here, we can say, look, our function f of xy is continuous inside this enclosure. So I'm continuous inside here. All right, great. And so what does that mean? Well, the great aha is to say, well, what that means is really we can compute y prime. Why? Well, because y prime is the function f of xy, and it's continuous in this region, and therefore it can be computed. And since I can compute it, I can say, all right, I can say what's the derivative at every single point, and now I can extend. And so our function can be extended in some way by saying, because we know where we start, we know how the derivative behaves, and therefore we can extend. Now, we may not be able to even extend it all the way to where the function is continuous, but we're just saying nearby. So our intuition says, look, we can start at a place, and because our function is continuous, we have a nice derivative that's defined that allows us to extend it for at least a short time. That's our intuition. That's why it's true. Okay, now, second point. See, the first point says something exists. The second point says a little bit stronger. So now, if we say, look, suppose you look at this function, partial f partial y. Now, we've talked about partial derivatives before, so let's just recall what they are. It means that we think of this function, it's really a function of two variables, and we say, okay, we're taking a derivative, but we're taking the derivative just of the stuff which has y's. Everything where we see an x, all the x's we treat like numbers. We treat those like constants. So like the derivative of x squared with respect to y is 0. The derivative of y squared with respect to y, 2y. So, all right. So it's not so bad to take partial derivatives with respect to y. So we say, okay, if this sort of extra condition holds, where the partial derivative is continuous, and you might say, in some sense, that means our function as a function of y is smooth, so differentiable means smooth. Okay, so if that is also continuous near our point, then it says, look, there is a unique solution. And I can see I have a typo here. Then there's a unique solution. Now, we should pause here and say, wow, cool. And the reason we should say, wow, cool, says this guarantees existence, this one guarantees uniqueness. Now, if you're not continuous, you're definitely not differentiable. And so this is really a stronger statement. If we can talk about the partial derivative being differentiable, then we say, okay, wow, that must have something going on here. Okay, and so this will, again, near our point, this is a unique solution. Now, it's possible that there's a place where the function is either not differentiable or not continuous far away, which can cause us to lose our uniqueness. We saw examples like this, where if you remember from our previous lecture, we had a situation where we had all the solutions passing through the origin, right? And we said, look, all the solutions look like some constant x to the fourth. So what that says is, yeah, nearby we have a unique solution over here, but we lose uniqueness when we come over to this part there. And if you remember what that differential equation was, it says the following. Well, suppose you look at x, y prime is equal to 4y. Right? That's the differential equation where all the solutions look like some constant x to the fourth. And say, hey, this is fine. Now, this is not written in normal form, right? How do we write it in normal form? Well, we write it as y prime equals 4y over x. That's what we mean to put into normal form. And now you see, oh, yeah, at x equals 0, there's a definite big problem with continuity, differentiability, hopeless, right? But away from 0, yeah, no problem. Which means that we're confident that if we start away from 0, nearby we have a unique solution. But once we hit 0, we lose that uniqueness. We definitely lose the guarantee of uniqueness, and in this particular case, we did in fact lose uniqueness as well. Now there's another note here that says, look, a solution might have other limiting factors. So, in other words, it might blow up, so it might have asymptotes. And we saw examples of this as well. So if you look at y prime equals y squared, that's a nice differential equation. See, this y squared, that's our f of xy. That's a really great function. It's continuous. Take derivative with respect to y. That's continuous. Life is good. We like this function. And so we say, hey, no matter where we start, no matter what our initial condition is, there's always a solution nearby. But having a solution nearby at any given point does not mean that we have a solution that works for everywhere, because some things can blow up. So in particular, if we have this initial condition y of 0 equals 1, you can check that our solution, y of x, is 1 over 1 minus x. And the reason I say you can check, we'll plug in 0, you get 1. On the other hand, if you take the derivative of 1 over 1 minus x, it'll be 1 over 1 minus x squared. Well, that's the square of the function you started with. So y prime equals y squared. All right, now what do you notice? Well, this function has an asymptote at x equals 1. And so it does the following. Here's x equals 1, and then we come like that. And so our initial condition says, look, we're fine locally, but we can only extend the solution for all values below 1, because we cannot push a solution past an asymptote. Differential equations, the curves have to connect, because we're starting by saying start here, move this way. So I can't say I move and then I do this big infinite jump. That's not how things work. So whenever there's a break in the curve, that says, look, solutions don't work. You got to give it up. Okay, so there's our background fact. So if we have these nice conditions, continuous, all right, something exists, partial derivative, also continuous, it's unique. Notice these statements here are if statements. They're not if and only if, which means that, well, just because something is not continuous or just because something maybe doesn't have a partial derivative doesn't mean that we're not going to have a solution, or doesn't mean that the solution is not going to be unique. It's just we're not guaranteed it. So please remember that as we go through and do the next example, which says, hey, let's try this fact out. Let's see if we can follow through on what we just learned, right? That'd be good. Can we learn what we just talked about? So we have a collection of initial value problems, all right? Boom, right there. And we're going to use the fact to decide when a solution or uniqueness is guaranteed. So really, does it exist? If it exists, is there only one? Okay, so what are we looking for? Well, we're looking for y prime equals this function, and we're going to say, is this a nice function? And when we take derivative with respect to y, is it a nice function? And those are the questions. All right, well, let's take a look. Okay, 2x cubed plus y squared. Is that a nice function? Yeah, we love polynomials. Polynomials are some of the nicest functions. They're the kind of functions that you'd love to take home to meet your family, because they'd be like, what a lovely function you met at university. I'm so proud of you. I'm so delighted. All right, so this is a beautiful function. So does a solution exist? And is it unique? The answer is yes. These are great functions because the function is a nice continuous function. Take the derivative of a polynomial, you get a polynomial, and they're nice and continuous. In this case, what is the derivative? We should practice a little bit, right? When we take the derivative with respect to y, 2x cubed goes away. Derivative of y squared is 2y. That's nice. All right. So yes, it exists. Yes, it's unique. Okay, the next one. So y prime is the square root of x minus y. Now the square root, that can get a little bit dicey, right? Because the square root isn't even defined for all numbers. We can only take square roots of things which are greater than or equal to 0. But let's look at our initial conditions. Y of 3 equals negative 2, which means when we plug in a positive 3, out comes a negative 2. So if we think about what's going on here, we say, hey, this is the square root of x minus y, and where we're at, so near this point 3, negative 2, our input is near what value? Well, it's near 3 minus minus 2. Our input is near 5. And now the question becomes, okay, is the square root function continuous near 5? Yeah, no problem. 5 is fine. It's when we get close to 0, things are like, so yes, we exist. Is it unique? Well, okay, what happens if you take the derivative? Well, the derivative of a square root function looks a lot like 1 over a square root function. And so if we were actually doing this properly, so we would say in a calculus way, this looks like x minus y to the 1/2. So the derivative would be 1/2 x minus y to the minus 1/2 times the derivative of the inside, which is minus 1. But the key is the constants don't really matter. It's what is this behavior? And that behavior is like 1 over a square root. And now, what are we near? Well, again, we're still near 5. That seems fine. No problems. No problems. So yeah, it exists and it's unique nearby, right? Remember, we only care about nearby, so we don't need to worry about things that might happen far away. Now the next one is very similar. The only thing that's changing is our initial condition. So instead of being at the point 3 minus 2, we're going to be at the point 1, 1. So do initial conditions matter in some sense? And not surprisingly, the answer is yes, initial conditions matter a lot. Because now what happens? See, now what happens is we can say, well, wait, if we are near point 1, 1, our input, what are we close to? Our input is near 1 minus 1, which means our input is near 0. Is the square root function continuous near 0? And the answer is no, because it's not even defined for negatives, which are right next to zeros. And if you look at the derivative, 1 over a square root, now that's like a 0. Wow, really bad. And so, does it exist? No. Unique? No. Now, when we say no here, remember what we're saying is we're not guaranteed. We'll come back to that statement in just a little bit. All right, well, here's another lovely looking one. Y prime equals 4x minus 4. Y of 1 equals 0. All right, beautiful, right? Polynomial. Life should be good, right? Right? Be careful. What's wrong with this problem as it's currently written? Well, notice it's not in the form y prime equals something. So in other words, it's not the normal form. So how do we fix it? Well, we move the y over. So we say, okay, really, this should be y prime equals 4x minus 4 over y. And now we see, hopeless, right? Because we're near x equals 1, y equals 0. That's like a 0 over 0. Forget it. Forget it. We can't say anything about whether it exists. And if we can't say anything about whether it exists, we definitely can't say if it's unique. So if we get a no here, automatic no there. So no, no. Wow. Rough crowd, right? Well, yeah, we're tough. We're tough because we want to make sure. You know, that's mathematicians spend a lot of time exploring, saying, look, how do we know? Why do we know? And so it's good. We're benefiting from their explorations. Okay, so the next two are again a pair that are very similar. So it's the fifth root of y. Now, if you're not familiar with the fifth root of y function, it looks something like this. It kind of looks like the cubed root of y, but more fifth root-like. But you can also think of it as it just sort of moves along this way. And it's a nice continuous function. So we say, okay, great. It's actually continuous everywhere. And so that's wonderful news. So since this is a continuous function, then we're going to get existence is yes. Because, look, no matter what choice for y you pick, it's a continuous function. And x doesn't influence it at all. Is it unique? Well, let's be careful here. So think about the derivative of y to the 1/5. What would that look like? Well, it'd be 1/5 and then y minus 4/5, which means that negative exponent means it's really downstairs. Now, we're okay with things being downstairs as long as what's not down there. We can't have 0 down there. So, what would be bad? Well, what would be bad is if we had an initial condition where our y value were 0. As long as we're not that, then we're great. So notice that in this case, our y value initial condition is positive 3. Wonderful. That's not 0. So yeah, unique. But here, 0. So that means we are not guaranteed a unique solution. So it's possible to say, look, yeah, something exists, but you might lose uniqueness. So just be aware that that's a possibility. So now we've seen all 3 of the possibilities that we can see. Yes, yes, no, no, yes, no. There is no yes, because we can't say, oh, a solution is unique if we can't even say, oh, a solution exists. So, all right. That leaves us with one last one, our final one. Okay, so let's look at this one. You might say, we see, sneaky, sneaky, xy prime equals 3y. All right, well, we got to rewrite it. So this is really y prime equals 3y over x. You say, aha, again, it's one of these. Look, hopeless, hopeless, right? Because we're at 0, 0. 0 over 0, forget it. Can't say anything. We don't know what it is. So we can't make any conclusions about whether something exists or whether it's unique. Great. Now, before we leave, let's look at this last one a little bit more. xy prime equals 3y, y of 0 equals 0. Do we see a solution that works? Can you see one? Well, oftentimes you say, well, let's try a super, super easy one. And here's a super, super easy one. What if you set y equals the constant function 0? Now notice, derivative of 0 is 0, 3 times 0 is 0, and plug 0 into the 0 function, you get 0 out. So here is a solution. In fact, there's more solutions than that. Another solution would be y equals x cubed. And again, it's a very easy check. I'll let you go through and do that on your own. But notice, there is a solution to this differential equation, but we wrote down no. So how is it that we said, oh, existence, we put a no, but actually there does exist one? And so now it comes back to what we're trying to do. Look at what the question asks us to do. It says, hey, use the fact and say if it's guaranteed. So the fact is not it must be the case. So another way to think about this is there are sort of 2 notions. There's necessary and sufficient. So what we have are some sufficient conditions to say, hey, if we're continuous, that's sufficient to say something exists. If it's unique, that's the partial derivative is also continuous, on top of that, that's enough to guarantee it's unique. And so, but it doesn't mean it's necessary. So strange things can happen. So just keep in mind that the basic fact says when things are guaranteed to exist, but there might still be some situations where things still somehow exist. As they say, life finds a way, right? And so maybe here it's solutions to differential equations find a way. So there we go. All right, well, lots of good practice, and we'll keep doing more practice. Lots of fun topics coming up in the near future, including opening up our black box that we've been using many, many times. That's going to be good. So please come back, and I hope to see you again soon.